All right, welcome everybody. This is the APES exam review for Unit 6 through 9. We are just 2 days out from the APES exam, so it's great to see so many APES scholars here ready to do some reviewing. Now, a couple things I want to touch on before we get into Unit 6 through 9. A little bit of 5 that we left over from yesterday. First of all, the chat is going crazy here. We have so many people. It's awesome to see. You can go ahead and leave a message where you're studying from. I always think it's fun to see, people from Dubai last year. We had a teacher from China last night. Usually we have lots of representation from all 50 states. So it's fun to see where people are studying from. So go ahead and let people know who you are, where you're studying from. Also, if you're watching this and you can't comment, part of the issue is you need to be a subscriber. So you need to subscribe to the channel if you're going to comment. We've had some kind of trolls in the past, and so we also have Kyra as our moderator. So if Kyra sees you posting things that are obnoxious or spammy, she's going to just delete that and maybe put you on timeout. So let's be focused here. It's great to ask questions in the chat. It's great to make some apes jokes here and there, but we want to stay focused, and we want to make sure that we're getting the most out of this review together. The first order of business, though, and I should have thrown his comment up. Now it's buried, so I have to find it. Where is he? Okay, so we're just gonna. I think this is Armando saying, the ultimate review packet was something useful, but I want to give Armando a shout out actually. So Armando and his teacher, Dr. McGraw, from Coral Reef Senior High in Miami, Florida. We want to give you a shout out to all of Dr. McGraw's classes. And Dr. McGraw, as I understand it, you are APE scholars of the highest order. And Armando Ruiz is one of you. And it's awesome to see the dedication. Good luck specifically to those awesome scholars down in Miami, Florida. To all APE scholars, though, of course, good luck. So I wanted to give a little shout out there at the beginning. Armando's been super, super dedicated to the channel all throughout. It's always fun to see. So what we're going to do is really quickly touch on a couple things before we actually dive into Unit 6 through 9. So a few people have been talking about the Ultimate Review Packet. The Ultimate Review Packet is a review packet or product basically that I've made with some other APES teachers who are exam writers. So they actually know the exam inside and out. And it's also something that's produced in a lot of other subjects. So if you guys know Steve Heimler from Heimler's History, he covers all the history courses for you. If you know Jacob Clifford from Econ and Crash Course, if you know Professor Dave Explains, there's a chemistry ultimate review packet. There's tons of ultimate review packets. But what I want to do really quickly is share with you guys what you'll get if you check out the APES ultimate review packet. You will get review for all 9 units. It's about 4.5 hours of video. So if you're wondering, is it something I can still do? Is it something that is worth buying right now, or is it a waste of time? It's 4.5 hours of video. So if you have, 10 hours that you're still looking to dedicate to this between now and that Tuesday morning, it could still totally be worth your while. The other thing is that I really appreciate the people who've purchased the Ultimate Review Packet and have supported this awesome project that I was fortunate enough to work on with, again, really talented video editor from Heimler's History and some other awesome APES teachers. If you have purchased this as a token of my gratitude to you, we're going to do an exclusive live stream. So this will be tomorrow from 7 to 8 p.m. Eastern. It will be an exclusive live stream just for the Ultimate Review Packet. It'll be a little more laid back. It'll be more of like a question and atmosphere. That doesn't quite work. Questions about the atmosphere. It'll be a question and answer type of setting. And so if you've purchased the Ultimate Review Packet, just an added little bonus. I will also be live tomorrow night on the Mark Learning YouTube channel from 6 to 7. And I'll make sure to post on all my socials and on my YouTube channel to let you guys know. But that, one more time, that Ultimate Review Packet live stream tomorrow is just for Ultimate Review Packet purchasers. Again, I just really want to thank them. It's been so cool to make this and see so many people use it. So as an added bonus, you get a little extra live stream review if you check that out tomorrow. But what we're here for today is, as someone mentioned, Unit 5, the end of unit 5 from last night, and then 6, 7, and 8. So we don't have a ton of time to get through that all. So let's get into it here. I will switch back over to some slides here, and we're going to start off with an APES math formula slide. Now, this is really important. These are the 4 formulas that you need to know. And I did a TikTok earlier today where you can see how to program these into your calculator so you don't have to memorize them. If you're not on TikTok, go check it out. Or if you don't want to use TikTok, I understand. I will try to pull those videos off TikTok and throw them up on YouTube as just a YouTube video. So that way, if you don't want to, do TikTok, you can still see it here. But these are the 4 formulas you need to know. These slides will be in my link tree at the end of this. If you're watching the replay, the slides in this will be in my link tree. They're not in there yet. I have to get them in there later. But anyway, these are the 4 formulas you have to know. There's a whole video on math. If you're struggling with math, that is something to check out. So, good question here. Will we make it to Unit 9 today? Julie asked a good question. You guys, let's actually do this backwards. So, let's start at Unit 9 because I don't want to run out of time. I don't want to run out of time. It's scheduled from 7 to 8. We have another question in the chat. How long is this scheduled to go? I scheduled it from 7 to 8. We can go a little past 8, but we can't push it to 9 like last night. I've got school tomorrow morning. So we've got to, I've got to get to bed and got my own APE scholars to teach in the morning. So yeah, we'll go to, 8:30-ish. We should be able to finish Unit 5, and we can put some extra focus on 6. So we'll actually go in order of importance: 9, 6, and then we'll go 5, and then we'll end with 7, 8. So we'll go out of order because it will be in order of ranking, meaning like how critical is it for the exam. So grab a hot beverage, maybe some tea, coffee if you're planning to stay up really late tonight, or some water. And I'm gonna have a little tea with lemon here. Easy on the vocal cords. And yes, this will be recorded. And so this will be something you can go back to and check out later. All right, without further ado, let's hide our banner so it doesn't cover stuff we need. And let's get into it here. We're going to skip, like I said, all the way back to Unit 9. We're going to actually do this out of order. So here we go. 9.1 is anthropogenic ozone depletion. So how do we break down the ozone layer that's up in the stratosphere, protecting us from the sun? We put CFCs, chlorofluorocarbons, up there. These are chemicals that used to be used in refrigerators or hairsprays. And when UV radiation hits the CFC, a chlorine atom breaks off. That's this red molecule here. That chlorine atom rips an ozone off. Rips an molecule. A little bit of an instability in our stream, so sorry about that. But hopefully we stay nice and smooth throughout. Yeah, it lags a little. I think what we can do is I can close my other computer here and see if that helps. That should put fewer items, less bandwidth on the system. So let's just shut that off. And maybe we'll make an upgrade in the internet here eventually. Yeah, let's get back through that because it did lag. So you have CFCs, the UV radiation hits them. This is UVC. It breaks off a chlorine atom. That chlorine atom, the red molecule, is going to bind to an oxygen, and that chlorine atom is going to pull the oxygen off, and now we've converted ozone into O2 and a chlorine monoxide. And the problem here is that this red chlorine molecule does this over and over and over again for millions of years. And it can, I'm sorry, not millions of years, up to 50 to 100 years. You can do it 100,000 times. It's just going to destroy tons and tons of ozone. So that's going to be a problem. What did we do about the problem? Well, we passed the Montreal Protocol. So the Montreal Protocol was this really successful international agreement, and we phased out CFCs. We replaced them with HCFCs, and adding an H or a hydrogen on means that they are less ozone depleting, so they don't detach that chlorine quite as easily, and that chlorine doesn't break down ozone quite as easily. And then eventually, just last year or 2020, 2021, we transitioned from HCFCs to HFCs. And now we got rid of the chlorine so they don't degrade the ozone layer anymore. So this is a great example of a solution that worked. Now we need to cover the greenhouse effect. So the greenhouse effect is this idea that we have all these gases in Earth's atmosphere that are heat trapping. We have CO2, we have methane, nitrous oxide, CFCs, water vapor is actually a greenhouse gas. And what I like about this diagram is that we have this visible light in yellow coming in and it hits Earth's surface and then it comes off as infrared radiation. So those red squigglies are infrared radiation, which we feel is heat. And that's why Earth's atmosphere is warmed. Without the greenhouse effect, Earth would be freezing cold. The problem is as we add more and more and more CO2 into the atmosphere or other greenhouse gases, it gets hotter because it traps more heat. Understanding the basic mechanism, though, of visible light from the sun be converted to infrared radiation by Earth's surface and then trapped by greenhouse gases is key. Lots of people know Earth gets warmer because of more CO2. Not as many people understand that the CO2 actually absorbs the infrared radiation and emits it or radiates it back down towards Earth. All right. The problem here with that rise in CO2, rise in greenhouse gas concentration, is we get a rising sea level. Again, an identified level or a base level understanding of this is warmer planet means higher ocean level or sea level rise. But the fives and fours among you, the people that are really going to be at that next level, are going to be able to explain that is because of thermal expansion and melting ice sheets and glacial ice. And then the big pro tip here, this is actually from an FRQ that people made a mistake on years ago. The ape scholars that wrote this, a lot of them wrote that the North Pole melting, so like polar ice, will lead to sea level rise, but it has to be ice that's on land. If it's polar ice in the North Pole, it's already in the water. So it has to be polar ice that's like on the South Pole, continental ice, or ice sheets or glaciers. And then thermal expansion is this idea that this tea that I just heated, the water molecules in here are spreading out because of the heat that was added by the boiling. And that's going to cause sea level to rise. It's actually going to be a little taller because each molecule is spaced out. And that means they take up more total space. All right, Big T is going to get a shout out here. Positive feedback loop with melting ice sheets. Absolutely. Big T took the words right out of my mouth. There's two positive feedback loops. I only have one in this slide here. But a positive feedback loop means that it gets hotter, that melts more sea ice. That sea ice reflects less light and leads to more dark blue ocean that absorbs light and heats the water and melts more ice. It reinforces itself. The same thing happens with something called the permafrost. In the permafrost, we have this permanently frozen tundra soil. But the problem is it being frozen year round means that there's a lot of methane trapped beneath it because as it starts to thaw, we have this standing water and all this grass and roots and organic matter that decomposes anaerobically, no oxygen. That means it's going to produce methane. That methane gets trapped in these big bubbles underneath the ground. So if you go Google later, methane tundra, you can actually see grass that's like wobbly because of the methane bubbles beneath it. And when that grass is punctured or when that ice melts all the way, that methane escapes, heats the planet more, which causes more permafrost melt. So it's this self-reinforcing loop of permafrost melt leading to hotter atmospheric temperatures. And then that also contributes to sea level rise. So well done, Big T. All right, what's another problem? Coral bleaching. As the atmosphere warms, so do the oceans. The problem here is that the algae that live in the reef, it's a mutualistic relationship. This is a callback to Unit 1, a symbiotic mutualistic relationship. So algae and coral live together in the reef. The algae provide energy via sugar that they produce via photosynthesis. The coral, which is a tiny little animal, it's the individual is called a polyp. And what it does is it produces CO2 through respiration, but it also leaves some little nutrients or dead organic matter for the algae, and they use it to create the sugar. And it's this mutualistic relationship. They both benefit. The problem is as the water gets hot, the algae can't stand the hot water and they leave And so the reef loses its color. So if you look up coral bleaching, you Google it, you'll see these white crusty coral that are weak and stressed because they don't have the energy they need. It's kind of like ape scholars without, YouTube resources or live streams for you. They're weak and stressed because they don't have quality resources. And we have a symbiotic mutualistic relationship here. I love making apes content and having a YouTube channel and sharing that with you guys. And you come and benefit from the apes content. And, it's a mutualistic relationship. So just like the algae and the coral, we're benefiting each other. So when that temperature changes, though, like when it gets too late at night, I got to go to sleep. And so I leave the live stream just like that. The algae leave the coral reef when it gets too hot. Another thing that can do this is pollutants. So sediment pollution, pesticides, or oxybenzone, which is a chemical in sunscreen, that can cause the coral reef to become bleached as well. That can cause a problem here for these organisms. All right, we have a question that's come in. We have a handful of questions, actually. We're going to try to get to these here from Top. So thermal inversion, we'll try to touch on thermal inversion. We will actually get there in Unit 7. But ocean acidification, we're going to get right there to go through the ocean acidification, and we'll try to touch on the catalytic converter. So let's go to this next question, which is about ocean acidification. Perfect timing, right? So in ocean acidification, if we look through this here, what it means for the ocean is there's actually a greater H plus ion concentration. And so you have CO2 in the atmosphere. That CO2 dissolves into the water. CO2 plus H2O makes H2CO3 carbonic acid. And Danielle gets a shout out for being on the money here. Rip to the shelled animals. Do we know why, though? Let's go to a high level understanding of why. As we have the increase in H plus ion concentration in the ocean due to the acidification, that H plus ion binds with the carbonate ion. Now, if you really know your chemistry, you know that a shelled organism, a shelled animal, a mollusk, or the coral reef, it depends on calcium carbonate. Those are the two building blocks of its shell. So if you have an acidic ocean, you have all these H plus ions taking up the carbonate ion, making it not freely available because it's binding with it to form bicarbonate. Then you have a bunch of sad shelled organisms who get taken down by the H plus. There we go. Again, pro tip, what separates like 2s and 3s from 4s and 5s? It's understanding what acidity really means. Acidity means you have a high H plus ion concentration, low pH, high H plus ion concentration. That's why I put the scale in this slide. And so what that's going to do is take away the carbonate ion from those shelled organisms that need it, and they're going to get taken down, unfortunately, by this. Really good question here. Does CO2 contribute directly to thermal expansion? Indirectly, I would argue. Indirectly, because it heats the atmosphere, which heats the ocean, which causes thermal expansion. CO2 does directly contribute to acidification because CO2 in the atmosphere goes into the ocean. Now we have CO2 plus H2O is H2CO3, carbonic acid. We give off the H plus ion and we lower the pH of the ocean, make it more acidic. So there we go. You love to see it. Let's just get another pin here. High pH equals high H plus, high acidification, and low. Oh, I'm sorry. Actually, I hate to do it, Henry. I thought you were right, but we need low pH. So Henry, recomment low pH equals high H plus, low acidification. I need to prep that one more before I threw it up on screen. So one more time, low pH. So 1, 2, 3, low pH, really high H plus ion concentration, high acidification. Even an ocean that has a pH of like 7 is very, very acidic. Ocean pH is around 8.2. Okay, let's go on to invasive species. Invasive species have some key characteristics that make them invasive. Here we go. We'll give them a shot at redemption. Henry is correct. Low pH means high H plus ion concentration, high acidification. Very good. All right. And Debbie asks, why is the acidity bad in the ocean? Rip to the shelled organisms. That H plus ion concentration depletes the calcium carbonate shells that they live in, and they die or become stressed or become, unable to reproduce. Okay, invasives. Are all our selected species invasive? No, not at all. Most R selected species aren't invasive. Most species in general aren't invasive. Yes, and the I in HIPCO, very good. Oh, that's not what we meant to do. Yeah, look at all these apes nerds in one room. Shout out to Marco Learning in the chat. Always good to see them making appearance. So the I in HIPCO is invasive. I for invasive species. Invasives can drive natives to extinction. That can threaten biodiversity. But what makes them invasive? Really high biotic potential, fast breeding, low parental care. Remember, R selected, run away. So maybe one of these days I'll make a TikTok where it shows like a spider laying a bunch of eggs and that says R selected parents. And it's like, she's a runner, she's a track star. And they're like running away, and that's what the R selected species do. So anyway, Asian carp. Yeah, Asian carp L. This is a big invasive that's on its way to the Great Lakes. It's not there quite yet. Illinois DNR is keeping it at bay with electric fences underwater, but they're keeping it out. Zebra mussels. What is an invasive to remember? Zebra mussels. Zebra mussel L. The chat moves too fast to pin these things. Zebra mussels, as you can see attaching onto this boat motor here, this propeller, they are filter feeders. So they eat all the algae out of the water, and that makes the water really clear. But it also takes algae and other organisms away from, like microscopic, plankton or algae, takes them away from other organisms that would eat them. And so zebra mussels cause other native mussels to go to become endangered. The python here as well is definitely a invasive species in Florida. This python ate a cat. This python ate a deer. And so mammals in the Florida Everglades have become, they've seen population crash. The pythons are just running through there. Strategies to remove zebra mussel. Good question. Physically remove them from your boat. So see the boat here. If you get a power washer and, spray that zebra mussel off there. I don't know why I held the power washer like a gun like that. But if you power wash your boat and you spray the zebra mussels off, that's going to help prevent their spread. Ships can also discharge what's called their ballast water, big industrial ships that transport cargo across the oceans. They can discharge their ballast water before they enter the Great Lakes, which is actually how zebra mussels entered the US. Right in my backyard, I'm in Michigan, the Great Lakes state. Shout out to anybody from Michigan if you're a Michigander. Way to go. It's the shape that looks like a mitten. But zebra mussels entered the US right in our Great Lakes in Michigan. You hate to see it. Okay, on we go to protecting endangered. How do we protect these endangered species that get threatened by invasives or that get threatened by poaching? We can have armed guards try to prevent the poachers. You can have legislation, CITES, the convention, for the International Trade on Endangered Species. So they try to prevent the trade of endangered species internationally. Our version of CITES, the US version of this that just applies to us, is the Endangered Species Act. So the Endangered Species Act, we have this ability of the US Fish and Wildlife Service to purchase land and actually protect it, designate it like a protected habitat sanctuary or wildlife preserve to prevent poachers or to prevent development or to basically protect the homes of those endangered species. And then also you can always designate areas a national park or wildlife preserve and preserve the ecosystem where those organisms are found. Alrighty, HIPCO. This is the last topic in Unit 9. So after this, we'll transition to Unit 6 with a brief stop at thermal inversions because we have a question. We had a question earlier from someone in the chat who really wanted to cover thermal inversion. So we'll make sure we get there. HIPCO, though, if you don't know HIPCO, you should know HIPCO. It's habitat loss, invasive species, population growth of humans, So urbanization, pollution or pollutants, climate change, and overexploitation. These are the causes. Who is? These are the causes that are responsible for biodiversity decline globally. So I put habitat loss and fragmentation towards the top, or I didn't. Whoever wrote HIPCO did, but it's at the top of this slide, so you can remember it's one of the biggest issues that that comes along with the cause of biodiversity loss. Sometimes I get sucked into the chat, and it's you guys are goofy. So invasives, we just talked about those. Population growth. So as human populations grow, we urbanize more areas, we build more concrete, we build more houses, we build more yards, and that takes away habitat and fragments habitat and kills organisms. Pollutants are a big one, especially for amphibians and reptiles that live in water. They're really at risk from pollutants that get into the water and can damage organisms there. So that's a problem. Atrazine, killing frogs, glyphosate killing aquatic plants or aquatic insects, can kill non-target species like bees that are beneficial. Climate change, of course, and then we have overexploitation. Overexploitation means overhunting. So the dodo bird went extinct, and we had, the passenger pigeon went extinct. Passenger pigeon or carrier pigeon? One of those pigeons went extinct. Fun fact, though, it went extinct at the Cincinnati Zoo, which is also the zoo where Harambe was killed. So it's like the Cincinnati Zoo really has gone through some loss of species that's been catastrophic. Okay, let us detour on our way to Unit 6. We'll stop at a confusing topic here, thermal inversion. So good question. Yes, let's just have a moment of peace for the dodo. The dodo is extinct. Jaden didn't know that, just learned it, I guess. And then also, as always, a rest in peace to Harambe. Gone too soon. Okay, Harambe really should be, like the mascot of apes. Maybe we need apes t-shirts with Harambe on them. It is sad. All right. Oh, we got another good comment. Thermal inversion isn't cap. Thermal inversion kind of is a cap, because that warm air caps the cold air beneath it. It traps it, and that traps pollutants down at ground level. So how does this happen? Well, it's especially likely in a geological basin, or geographical basin, maybe I should say, where you have this kind of mountainous region around a city, and then you can have a warmer, mid-latitude kind of air mass come in and trap colder beneath it, or a cold, higher latitude air mass come in and cover that warm air mass below. But when you get this thermal inversion, you have warm air trapped between cold air above and below. The cold air at the surface of the city can't rise, so it can't disperse those pollutants. So those pollutants do kind of stay capped below that warm air, and it's going to exacerbate or make worse asthma, bronchitis, all of those, issues that happen, respiratory issues, when you have pollutants trapped near Earth. Yeah, LA homies have definitely experienced a thermal inversion. You guys probably have days where, it's like an ozone action day, or even like a clean air action day, where they try to encourage you to take public transportation, stop driving so much, because that one is going to reduce the NOx that's emitted from your vehicles and the formation of ozone and smog. But two, it can hopefully help limit the effects of those thermal inversions that might occur on an especially hot day. So is thermal inversion important to know? Yeah, I mean, every topic could come up in the exam. It's not a majorly critical one. It's topic 7.3 if you want to go check it out. So that is a good topic to check out if you feel like it. Let's detour back through Unit 6, though now. Unit 6 is energy. It's a really big unit, important unit. So let's go through Unit 6. We also are going to, again, we're going to focus here on Unit 6, the high impact units. We had a request for the nitrogen cycle. Unfortunately, we covered the nitrogen cycle in the last live stream. We have a video on the nitrogen cycle. It's going to be 1.5. So let's just drop that in there. 1.5 nitrogen cycle. I know it's one that people are worried about. We had a specific question about it. I'll try to touch on it towards the end. We're going to keep rolling with Unit 6 right now because it's a really important one. So in Unit 6, we have these different energy sources. The two big categories of them, of course, are renewable and non-renewable. And it looks like Kyra maybe even linked in the doc there that was requested for the nitrogen cycle. So Seb Nation, check out that doc. Kyra's got you in the chat. She's looking out for you, trying to help make sure you know the nitrogen cycle. Oh, this is really interesting. Let's actually stop for a second. You caught my attention. Sammy Davis Jacobs. I remember the nitrogen cycle as fix, NAAD, and PAN. I don't know this acronym, but I kind of want to guess it. And again, sorry for the sidebar, but this is a good comment. So fixation. My guess is the A and A stand for ammonia and ammonia and ammonium. I'm not positive what the D stands for. I mean, there's fixation, and then there's nitrification, ammonification, denitrification. I don't know what it all stands for. Why don't we get Sammy Davis Jacobs to drop that in the chat? Drop in what that whole acronym is for us, because I've not actually seen this. This is really interesting, though. And I would love to give people good acronym for the nitrogen cycle. So Sammy Davis, it's your time to shine. Hit us with that nitrogen cycle acronym and carry the APE scholars for Unit 1. All right. On we go. Oh, Natalie says fixation, nitrification, assimilation, ammonification, denitrification. That makes sense. I guess I was a little hung up on the last few letters, like the NAND at the end. ANPAN. Ammonia, nitrogen, or atmosphere. Yeah, I don't know. What's the ANPAN? Someone help us out with the ANPAN. Because I'm not sure where the ANPAN comes from. But shout out there. And yes, you learn something every day, even if you're a teacher. So thank you for that. Excellent stuff. On we go to the energy we need to cover in Unit 6. So here's the key. Fossil fuels are unsustainable because they are used faster than they're regenerated. So I'll say that again. They get used faster than they get regenerated, and so they will not last. All right, here is our ANPAN at the end. Atmosphere, nitrogen, proteins, ammonia, nitrogen. Kind of the forms they're existing in, I guess. So they're in the atmosphere, then it's, nitrogen in the soil, then they get taken into plant proteins, then it gets turned into ammonia back into the soil, and then it's denitrification, converted into nitrogen gas again, N2. That's good. All right, let's keep it moving though. We need to know fossil fuels are the biggest source of energy globally by far. But you also want to know the three types and what they're used for. So with oil, obviously with oil, obviously gasoline in your car, that's going to be the number one source or use of oil. But then we have coal. That's our main source of electricity generation globally, although natural gas is gaining on it because it burns cleaner, produces fewer pollutants. And then we have natural gas, which is also used in furnaces to heat homes. So those are big uses you should know. Hydroelectric is the biggest renewable by far. And then we have nuclear as the third largest source globally. Nuclear is non-renewable, but it does not emit air pollutants. And so we'll talk about what that means here shortly. Talk about why nuclear is kind of in a class of its own. Coal formation really quickly. You have bogs, peat, this partially decomposed organic matter. And typically you're going to find coal really anywhere that you had dead organic matter, like plants that were on land. They get compressed over time. And then we have different gradations of them. So there's lignite, bituminous, and anthracite in order from least energy dense to most energy dense. So A, anthracite, beginning of the alphabet, most energy dense. It's going to burn cleaner, burn longer, produce more electricity. The problem with coal is it's the dirtiest fossil fuel. It's going to produce the most PM, soot, SOx, NOx, particulate matter. It's going to be the most polluting. It's going to release the most pollutants and the most CO2. Then we have natural gas. Natural gas is the cleanest fossil fuel by far. It is the decaying matter of plants and animals again, sometimes marine life. And the trick here is it's mostly methane. So it's a little bit different than coal. It's not a solid. It's going to exist in a gas, often found on top of oil. And then again, the big thing you need to know is it's going to produce about half as much CO2. It's going to produce way fewer units of air pollution of all the rest of these air pollutants. So it produces virtually no SOx. It's going to produce a little bit of NOx, a little bit of carbon monoxide, a little bit of particulate, but basically none when compared to all of these other fossil fuels. Yes, coal, not a great energy source to use. Although it's cheap, it's readily available, there's lots of it, so that's why we use it. But we should use less if we want to reduce air pollutants and mitigate climate change. Now let's get on to oil, which is the one we haven't really talked about yet. Oil is kind of in the middle. It's an intermediate fuel in terms of its energy density not its energy density, it's pollution release. So it's going to release a medium amount of pollutants compared to natural gas and coal. How do we get it? Typically, we drill it out of the ground, but sometimes it's extracted with tar sands. So tar sands are these thick, viscous, kind of sticky deposits that are combinations of clay, sand, water, and something called bitumen. And so bitumen is going to be this thick, basically tar. Like if you've ever seen tar on the road, bitumen is actually part of that process of making tar that goes on roads. And so it's going to be this thick, kind of semi-liquid, semi-solid, definitely not ready to go into your gas tank yet. So we have to pump a bunch of hot water or steam into it, loosen it up so it can flow up to the surface. So tar sands is a way of getting low quality oil, but you have to use a bunch of steam and you have to use a bunch of hot water. So it takes lots of energy and lots of it is going to be done in Canada. Yeah, it's popular in Alberta, Canada specifically. Something you should know. It's going to be they're going to be the number one tar sands producers globally. So just a way to extract low quality crude oil. We go to how do we actually make electricity? Anytime you burn something, anytime there's a combustion reaction, we have this series of emojis here that you can see on the screen. So you're going to have heat. That heat is going to turn water into steam. That steam is going to spin a turbine. That turbine is connected to an electrical generator that produces electricity from the kinetic motion of that spinning turbine. It now gets converted into electrical energy by the magnets that are inside that electromagnetic generator. This is how we actually get electricity. This right here is one of the most important slides in all of this slide deck, because after you take that heat source, you can do the same process, whether you're burning trash, whether you're burning wood, whether you're burning coal or oil even. And the same process happens with nuclear, except instead of burning something, you're producing a bunch of heat through a fission reaction. So let's go to nuclear here and take a look at it. So in nuclear, it's the same process. It's heat turning water into steam, steam turning a turbine, the turbine, spinning kinetic energy, and the electrical generator connected to it, converting that spinning kinetic energy, or mechanical energy, sometimes we'd call it, of the turbine into electrical current. The heat is different. The heat comes from a fission reaction, typically with uranium-235. How does this work? Well, if you look at this diagram, we have a fuel rod, and the fuel rod is where the uranium is stored. That generates a tremendous amount of heat. That heat is used to turn water into steam. That steam turns a turbine, and the rest of the drill. Now we have a cooling tower here that's going to allow that steam to evaporate so it can lose some of its heat so it can cool down and be reused again. Because you can't just keep hot water going or it doesn't pick up any new energy from the nuclear reactor core. And your core is actually going to get too hot and it can melt down. So if a meltdown, takes place, then you lose the control of that, reaction, and you're going to release radiation. We have control rods that can be dropped down into the reactor core. they absorb the neutrons that are zooming around. And we had a quick question here about the how does the fission reaction occur? I don't have the slides up, but what you have is a really unstable nucleus of uranium-235, and you shoot a neutron at it. So you shoot this neutron into the core of this uranium-235 atom, and it splits. That's where the term fission comes from. A fissure is like a break or a split in something. So now that fissure happens, or that fission, I should say, the nucleus breaks, sends a bunch of other neutrons that break a bunch of more nuclei, and then we release huge amounts of heat in that process. All right, on we go to biomass. Biomass is a little different. So biomass, you have two basic ways to do this. One, you can just literally burn any organic matter that's combustible. If it has carbon in it, it can probably be burned. The drier, the better. And so you might burn logs, animal manure, charcoal, dead brush leaves, stuff like that. And that's going to be the number one source of heat in terms of the number of people globally that use it. So I'll say that again. An estimated 2 billion people, give or take a few hundred million, are using biomass as their primary source of heat and their primary source of cooking. It's cheap, it's easy to find, it's a subsistence fuel, so you can gather it from around your dwelling. We call it carbon neutral because that carbon was just taken out of the atmosphere by the plant that photosynthesized to take the carbon in. Now it's returned when we burn it. So we call it carbon neutral. So that was one thing I think is important to know here. It's considered carbon neutral. So meaning we're not adding new carbon to the atmosphere. The second way we can do this is through biofuels. This is taking something like corn or ethanol that comes from corn and burning it in an engine, a combustion engine, just like you would burn gasoline. And in fact, pretty much every car in America is burning some ethanol right now already. Almost all gasoline is already mixed with ethanol. And in some instances, it's actually called E85, and they make it really clear. But most gasoline already has some ethanol mixed in. You can also do biodiesel, which is a little different. That's more of like a plant oil, which is different than an alcohol like ethanol. But the same basic idea applies. You do fermentation or you do some sort of chemical transition to get that product out of the plant. Oil in the case of biodiesel, alcohol in the case of fermenting sugar from corn, and you burn it in place of gasoline. All right, solar energy. Solar energy is great in the sense that there's no CO2 release and there's no air pollution, no PM, SOx, NOx, but it is going to have some drawbacks, which is that it can disrupt habitats, especially in desert ecosystems. And then the silicone that goes into it is a limited resource. So you can't necessarily make solar panels without having any environmental impact. There's environmental impact from the mining of silicone. But at the actual point of electricity generation, you're not going to produce electricity. You're not going to produce particulate matter or pollutants as a result of producing the electricity. And you are not going to generate CO2 either as a result. So huge advantage there. Then we have water impoundment, which is a fancy word for dams. And the trick with a dam is that you need to build a reservoir. So you stop the natural flow of river, and then you build up a bunch of potential energy in this reservoir. Now that potential energy can rush through this gate or this channel at the bottom, spin a turbine. Turbine's connected to a generator. Hopefully at this point, you guys, that sequence is tried and true. You know how that works. But the idea, and you need to understand this was actually on the 2021 FRQ set, is you need to know that it's the potential energy of that water being stored at a higher level that allows it to rush down through the intake channel by the force of gravity pulling it down. That's what causes it to spin the turbine. All right. A problem with dams, though, is they stop sediment from migrating downstream, and they also stop fish from migrating upstream. So I'll say that again. They stop sediment, which has nutrients in it, from going downstream to wetlands or other habitats. They stop fish from migrating upstream. That's going to reduce the efficiency of your dam because there's just less water in the reservoir. It's also going to lead to a warmer reservoir. You have all this surface space that's heated by the sun. There's evaporation. Less total water in the reservoir means less energy production. How do you solve that issue? With the salmon cannon. You catch the fish and you put them in this thing and it shoots them up over the dam, or you can do fishy stairs, which I sadly don't have a picture of, and we have to keep moving, but go ahead and search fish stairs or fish ladder and you'll see these awesome pictures and videos of a really cool solution. All right, geothermal really quickly is this idea that we can go down into the earth and get heat from near the Earth's core. Not really near the Earth's core, actually. It's really far away from the Earth's core, but we can get to hot rocks that are heated by the mantle, the heat from the Earth's core. Then we can pipe it up to the surface and spin a turbine with the steam that we create. Benefits are it's renewable if we keep recycling the water. There's going to be a lot less CO2 and there's no air pollutants. But the drawbacks is hydrogen sulfide. You should know that hydrogen sulfide can be released from geothermal. That can be poisonous to humans, but also you just can't do geothermal everywhere. So geothermal can only be accessed in certain regions, especially areas near active tectonic plate boundaries like California or the Western US. So where I live in Michigan, wouldn't really be feasible to build a geothermal plant. It's just too far underground. You'd have to drill to get to that hot rock to get that steam to turn into to turn the turbine. So it doesn't work everywhere. All right, here it is. Somebody asked for hydrogen fuel cells, and here we have them. So hydrogen is this fuel source that you can put hydrogen gas into a fuel cell. The electrons are going to be forced around this membrane that only lets the positively charged protons through. We call it an electrolyte membrane. So the H plus ion passes through, the electron takes an alternate current path around. That's what is an actual electrical circuit. It's electrons flowing, and then it reunites on the other side, and we produce only water as the byproduct. Inputs are hydrogen and oxygen, which of course is in the atmosphere around us. The hydrogen we have to produce, and then the H2O, water is the only output. So that is, a basically carbon neutral way to produce electricity as long as the hydrogen is produced sustainably. The problem is we produce most hydrogen with methane, steam reforming. So it's only as sustainable as the way you produce the hydrogen. But if you do hydrogen with electrolysis, you can produce clean hydrogen if that electricity came from a renewable. All right, now we're into the waviest form of energy, which is wind energy. Very similar to hydroelectric, but instead of falling water, also falling water is a great Maggie Rogers song. If you listen to Maggie Rogers or if you listen to that kind of indie music, check it out. It's just a beautiful song. But falling water of a dam is what, spins the turbine. In this case, it's the wind. It's the wind that's spinning that turbine. And that turbine is connected to an electrical generator, just like in hydroelectric electricity production. And that's going to be the way that we do this. If we put these turbines up in a windy field where we have lots of air moving, that is going to produce this electricity. Drawbacks, NIMBY, some people don't like them in their backyard. NIMBY stands for not in my backyard. And so people don't always love to see the big eyesore. I think they look pretty cool personally, but they are considered an eyesore on the APES exam. You can call them that, or you could say they produce noise pollution. There is actually a whirring from the rotor sometimes, and also rip to the to the bats and the birds. So a bird, especially a big migratory bird, can get smacked right out of the air by a wind turbine. So that is an issue there. Sadie says they can put as many wind turbines as they want in my backyard. Yes, in my backyard. So we also have YIMBY because here's the thing. If they put a coal-fired power plant in your backyard, going to produce a lot of pollutants, a lot of, particulate matter that you're going to breathe, a lot of SOx and NOx. So it's a trade-off. NIMBY definitely also happens with nuclear. People are afraid of a reaction releasing radiation. All right. Boy, I didn't know YIMBY was a thing. That's great. Final topic in Unit 6 is energy conservation. No, Tyler, you do not want to smoke the coal pack. That is bad for your lungs, and I don't recommend it. So, sustainable home design is a way to conserve energy by the way you build your home. So, one way you can do this is put a deciduous shade tree, meaning a big broadleaf like maple, or a tree that loses its leaves in the winter. So, it lets the sun through in the winter to warm your house. But in the summer, it leafs out and has this big shade that it casts on your home, and that saves on your cooling bill because your home is naturally cooled. You can also do double paned windows. Double paned windows will trap your heat in during the winter so that you don't lose as much of it and you don't have to pay as much money to heat your house. You don't have to use as much total energy to heat your house, as much natural gas. But then you also in the summer can trap in your cold air that you're producing. So that can help. Better insulation, more efficient insulation can help. And that's going to decrease how much electricity you have to use for your air conditioner. All right. What SOx and NOx? Oh, check out 7.1 for what SOx and NOx. Got to know those for sure. I'm going to take a break for a little tea, little honey and lemon in here, and then we'll keep it rolling. But take a look at some air pollutants in the meantime. All right, we have some great questions in the chat. I can't remember what kind of tea it was. It's kind of light pink. I grabbed it really quick, but it has lemon and honey. I feel like it's maybe a lavender. Not positive. Okay. This is now Unit 7. And 7 and 8 are not as weighted, meaning on the exam, they're only 7 to 8% of the exam, but they get tied into other units. So it is time to get into those now. Yeah, SOx is very mid. You don't want SOx in your air. So let's get into this. Why do you not want them? Well, for both SOx and NOx, you can have respiratory irritation. It can get into your throat and irritate it. I'll tell you what, after 2 nights in a row of numerous hours of live streaming, I feel like I've just inhaled NOx and SOx. It's brutal, but we've got a few more units to get through. We're going to keep rolling here. So when we look at sources, coal combustion is a big source of SOx and NOx. And that's why coal is really not the best energy source out there. It's one of the worst from an environmental standpoint. So another air pollutant, though, is carbon monoxide. This comes from incomplete combustion, especially if you have a furnace that is poorly ventilated. It's not being vented outside your house. That carbon monoxide can build up inside, and it can lead to asphyxiation or death due to suffocation. You don't want that. Then we have particulate matter. Particulate matter should be your ace in the hole, like ace up your sleeve. What do I go to if I don't have a answer for an air pollutant? Go to particulate matter. It's going to be things like soot, ash, dust, and particulates that come off a burning combustion reaction. Bad for your lungs. Then we have ozone. Ozone is a secondary air pollutant. So we'll get into what a secondary air pollutant is in a second. Then you also have lead, which can come from metal plants or waste incineration plants. And this is going to be a neurotoxicant, meaning it's going to damage your nervous system. All right. Primary and secondary air pollutants are important to understand the difference between. Primary air pollutants just come straight out of a smokestack or straight out of a tailpipe on a vehicle. So most pollutants are primary here. We have NOx, carbon monoxide, CO2, VOx, sulfur dioxide, and particulate matter. The reason I put an asterisk on CO2 is not an air pollutant from a, basically breathability standpoint or human health standpoint. We have Hassan, who remembers the oath. Hassan took the APE Scholar oath against pollution. Let's all take it now again just to be safe. I, APE Scholar of the highest order, solemnly swear that I will not use carbon dioxide as an air pollutant on the APES exam on Tuesday. because it doesn't count as an air pollutant on the APES exam. What do I mean by that? It doesn't lessen air quality from a breathability standpoint. It doesn't directly damage human lungs or plant tissue or animals. Obviously, it causes global warming, which indirectly threatens humans. And the EPA actually ruled through something called, or the Supreme Court ruled through something called the endangerment finding, that the EPA can regulate CO2 under the Clean Air Act, but College Board has not caught up and classified CO2 as an air pollutant. So don't call it an air pollutant. It's a greenhouse gas, which is different than an air pollutant. So again, greenhouse gases heat up the planet, cause a whole bunch of problems. Air pollutants do not heat up the planet, cause problems down at Earth's surface in our throats and lungs and eyes. They damage plant tissue, so different things. The EPA does care about CO2 and they do regulate it now, but it's not considered an air pollutant. So just keep that in mind. Secondary air pollutants have to undergo some sort of transformation or change in the atmosphere. So in the atmosphere, they combine with water or oxygen or sunlight, and you're going to form things like ozone from NOx. We're about to learn how that happens. Or you can form sulfuric acid or nitric acid from SOx and NOx. So SOx and NOx can both transform in the atmosphere to become secondary air pollutants like ozone or sulfuric and nitric acid. All right. On we go to how photochemical smog forms. So we have NO2, NOx. It's emitted by vehicles, primarily in urban areas, although electricity production by coal can also contribute NOx or NO2. Now, here's a tricky thing. Usually you can say NOx on the exam, but what you want to talk about if you're talking about smog formation is specifically NO2. It's not NOx. It's NO2 that has one of its oxygens broken off by the sunlight. So the sunlight hits NO2, an oxygen comes free. Now we have NO, nitric oxide, and a free oxygen. And that oxygen atom combines with O2, and now we have O3, three oxygen atoms together. Down in the troposphere, that irritates respiratory tracts, can damage eyes, can damage plant tissues, and it can combine with VOX, volatile organic compounds, to form photochemical smog. And the reason here is that normally this reaction is reversible. Normally the ozone just breaks down and the free oxygen goes right back to NO2 and the O2 molecule goes on its way. That doesn't happen though when you have VOX added to the equation. When VOX are added, they bind with that nitric oxide and they combine with ozone then to make photochemical smog. It's thick, cloudy, difficult to breathe in, difficult for sunlight to penetrate through. And so that is something that you should understand. Again, starts with NOx, sunlight breaks down the NO2 into NO and O, and then you have ozone, which is going to combine with the VOX and O2, and that's going to form photochemical smog. We have a quick question here. What are PANs? PANs are another class of compounds that can mix with ozone and lead to photochemical smog formation. So think, if you see PANs on the exam, you're like, what the heck is this? It's a super long, complicated acronym. Know that it goes with ozone and it contributes to photochemical smog. Don't panic about if you haven't heard about it. Just if you see that, think, okay, PANs, photochemical smog, contributes to it with the ozone formation. We're not going to get into the whole chemistry of that. On we go to the thermal inversion, which we already touched on. So we'll keep rolling. Natural sources of carbon dioxide and particulate matter. So remember that all living things respire, so they give off carbon dioxide, but it's not net carbon dioxide increase. So we have just the CO2 given off by organisms having just recently been in the atmosphere because it just went to a plant that organism ate. So although CO2 technically is, although respiration is technically a source of CO2, it does add CO2 to the atmosphere. It's typically taken right back out on a net balance by photosynthesis, by living plants. Then we have aerobic decomposition. That's the breakdown of organic matter in oxygen-rich conditions, which is going to contribute CO2 to the atmosphere. On the other hand, anaerobic decomposition, we talked about this with the permafrost. That's the breakdown of organic matter in low oxygen conditions where you have water, stagnant water gathering. That's going to produce methane that's going to go into the atmosphere and contribute to climate change. So make sure you understand that decomposition. If it's aerobic, it adds CO2 to the atmosphere. If it's anaerobic, it adds methane to the atmosphere. And whether it's aerobic or anaerobic depends on how much oxygen there is. Yes, are there any videos to help learn more in depth about SOx and NOx? Great question. This is going to be topic 7.1 and then go right into 7.2 for more review of photochemical smog. If you don't know SOx and NOx, I would definitely watch those videos between tonight and tomorrow. Remember that indoor air pollutants are going to differ vastly based on the different countries that we're talking about. So if we're talking about a developing nation, primarily we're looking at carbon monoxide, particulate matter, NOx and VOx coming from combustion of organic matter in the home. So poorly ventilated homes that don't necessarily have a chimney or a fan or a good ventilation system, they are going to be suffering a lot of times the effects of these pollutants building up in the home because biomass combustion is that number one fuel source or source for cooking and heating. Developed nations, on the other hand, or more developed nations like the United States, they're going to suffer more from asbestos, radon, mold, particulate matter, lead. Not yummy, though. You do not want to eat lead. But I did want to highlight that comment because Daniel's right. These are the pollutants that are most problematic in developed nations. So where do they come from? Let's just go really quickly through this. Asbestos comes from old insulation in the attic. Replace it with a trained professional. That's the solution. Radon comes from the breakdown of uranium in the soil or in the bedrock, especially granite, underneath your home, and it seeps up through the foundation. Seal the cracks in the foundation to prevent it from getting in. Mold comes from wet surfaces that stay wet and don't get dried out. They don't get ventilated underneath your floor, tile in your bathroom, behind your sink, behind the paneling in your shower. Those are places where you're going to run into mold development. How do you fix that? Increase the ventilation, seal those cracks so the water doesn't drip behind that area. How do we get lead in the home? Lead in the home comes from old paint or potentially old water pipes. And the way to remove that is to have lead professionally removed by a paint restoration specialist, basically, that can strip it off, use a ventilator so you don't inhale the lead, or replace the lead service lines that are giving your house water. This is especially a big issue in Flint, in Michigan, where I live. And so it's something that can be a neurotoxic and it can be damaging to the central nervous system, especially of small children. So unfortunately, it does cause learning disabilities, and it's not something you want in your home. How do we solve air pollution? How do we fix the issue? The reason that I want to review in this video laws and regulations instead of things like wet scrubbers, dry scrubbers, baghouse filters is I think that stuff is more straightforward. This stuff, meaning these laws and regulations, are a little bit trickier. So I would know these things because they're great solutions to air pollution. So the Clean Air Act, that gives the EPA the ability to monitor the release of those 6 criteria air pollutants that were a few slides back. So let's just go back for a second. The Clean Air Act specifically says the EPA has to set acceptable levels for these 6 air pollutants. And then if you as a company, as a power plant, or as a medical waste management company or something, if you're emitting more than the acceptable level of any of these pollutants, the EPA can come in and say, we're going to fine you or we're going to revoke your license. You're not going to be able to produce energy anymore because you're out of compliance. And so that's what the Clean Air Act does. You can make the Clean Air Act stricter. That would be a great way to have better enforcement and reduce air pollutants. If we go back here, we have a couple other pieces of legislation. You have the CAFE vehicle standards, corporate average fuel economy. So if you make the CAFE standards more strict or you raise them, what that does is means that vehicle manufacturers have to, on average, make their vehicles more fuel efficient. They have to go further on fewer miles, 50 miles per gallon, 60, 70, 80. You could ramp up the miles per gallon they're required to average across all the vehicles they make. That means less NO2 or NOx, less particulate matter, less carbon monoxide and carbon dioxide per unit or per mile, essentially. We had a question earlier about catalytic converters. I don't have catalytic converters in today's slides, but if you want more, this is going to be video 7.6 on my channel for catalytic converters, scrubbers, etc. So someone asked about that earlier. Just want to make sure you know where you can find more info. Basic idea of a catalytic converter is you're going to convert carbon monoxide, you're going to convert NO2, and you're going to trap harmful metals that may be in there. And you're going to, I'm sorry, you're not going to trap harmful metals. There are metals, palladium being one of them, in your catalytic converter that are going to convert the carbon monoxide into carbon dioxide, because carbon monoxide is poisonous to humans. They're also going to try to convert some of that nitrogen dioxide, the NO2 that's produced, into just N2 gas, which is not, damaging to air pollutant, or not an air pollutant, not damaging to the air that we breathe. And so again, catalytic converters convert harmful substances like carbon monoxide and NOx into less harmful substances like CO2 and N2. Why do we want to reduce NO2 coming from vehicles and SO2 coming from coal-fired power plants? Well, we already know that those are going to damage respiratory tracts, but they can also lead to acid rain. So up in the atmosphere, this is a great example of how a primary air pollutant like NO2 or SO2 transforms to become a secondary air pollutant. So they mix with oxygen and water in the atmosphere. Now they form nitric acid and sulfuric acid, and then they dissociate. They give off an H plus ion, and that H plus ion rains down towards Earth in a water droplet, and it can lead to acidification of the forest ecosystems that can damage trees. It can lead to the acidification of waters, which can kill organisms that have a narrow pH range or make toxic metals more soluble. It can get into soil. It can leach out nutrients. It can, decrease the ability of trees to withstand cold weather because they get less nutrients from the soil. Really problematic. And so the way to reduce this is to replace coal-fired power plants with either natural gas or with renewable energy, ideally, that doesn't release SO2. Drive less. So carpool, bike to work, raise the CAFE standards for vehicles. All of those things result in less NOx and therefore less acid deposition. All right, on we go really quickly to noise pollution. Noise pollution can be damaging to hearing. It can give you headaches and confusion and frustration. It can limit the communication ability of organisms that may need to migrate or hunt or hide from predators. And so urban areas that have traffic, that have lawnmowers, that have neighbors that stay up late and party like mine, that's going to lead to noise pollution. It's going to keep you from getting sleep, going to have adverse health effects for humans and for animals. So noise pollution is a real type of pollution. All right, I'm seeing a couple questions here about practice tests. So let's take a break because we're about to turn the corner into Unit 8, which is our last unit to cover. There are no official practice tests freely available. I think you can dig up the 1999 multiple choice practice, but it's so long ago, it's not accurate anymore. So just as a reminder, if you check out in my link tree, the ultimate review packet, you'll get 2 full-length practice tests that were written by real AP exam writers. These are really experienced APES teachers that I know personally that write for the College Board, and they wrote the practice tests. I worked with them to have them write the practice test because they're more experienced APES writers and APES teachers than anybody I know. And so they created 2 full-length practice exams, multiple choice with answer keys. So if you're looking for a full-length practice exam, you can do that. Another question though, what about AP Classroom? Absolutely. If your teacher assigns you an AP Classroom practice test, you can totally take that as well. I'm not trying to paint the picture that the Ultimate Review Packet is the only place to get one. Princeton Review has them, Barron's has them, AP Classroom has them, but you're not going to be able to just Google and find one. Your teacher would have to assign it to you, and really they're only supposed to assign it to you during class. And then, you could also get one from the Ultimate Review Packet or any of those other places that we just mentioned. All right, on we go to Unit 8. Hang on to your seats, everybody. This is the last unit we have to go through. And then we'll touch on a little bit of Unit 5. We are kind of going to fly between Unit 8, you guys, because I want to get to 5 a little bit still, and Unit 8's only I think 7 to 10% of the exam. So we got to fly. All right. On we go to point and non-point. Basic rule of thumb, if you can point at it, it's a point source pollutant. So if you could look at a smokestack or this discharge pipe, that's point source. Non-point could be sediment flowing from a big agricultural region, really hard to identify, or urban stormwater runoff. Non-point, who's to say who that piece of trash in a parking lot came from? It's too hard to tell where it came from. Point is going to be one singular point. Oil spills. Oil spills are point source pollutants if it's from a tanker or a blowout of an oil well, like the BP, what was it, Deepwater Horizon oil spill. How do we clean these up? What are kind of the issues here? So first, let's go through the issues and then talk about cleanup a little. The problem is that the hydrocarbons in petroleum are toxic to organisms. So they're going to be directly lethal. They're going to kill organisms. It could also decrease the visibility in the water so they can't hunt as well if they have to catch prey. It could clog the gills of fish or stick to the feathers of birds. You want to be able to give effects that are not just death. It's really easy to be like, it kills something. A lot of times that's not actually on the College Board rubric on an FRQ. So you want to go to sublethal effects like suffocation through choking on the oil, sticking to feathers, sticking to gills. Can also wash up on shore. That's going to decrease tourism revenue. It's going to get into mangrove swamps and get into salt marshes and kill those plants if it buries itself in the root system. So it's really problematic. How do you get rid of it? You can burn it. You just light it on fire and that will actually burn it. You can use boomers, skimmers, and physical removal. I love it when you guys answer your own questions. Shout out to Danny again. You're going to potentially even like vacuum it off the surface, almost like pull it off with like a suction hose, or contain it or kind of pick it up. And so that is, really, really effective at containing it. Yeah. Boomers. Bring in the boomers to clean up the oil spill. It probably is boomers working on the oil rigs, although they're getting close to retirement. Anyway, on we go to endocrine disruptors. Endocrine disruptors are a great example of a specific sublethal effect. So I'm going to say that phrase again because APES FRQs recently have started this trend of asking you to identify an effect other than death. They're like, listen, we know things can die. Give us an effect other than death, okay? And in this case, endocrine disruptors are a great example. They're going to disrupt the hormonal system or the reproductive system in a lot of cases of organisms. How do they do that? They bind to a receptor and mimic a hormone. They could upregulate, meaning amplify a hormonal signal, or downregulate and block a hormonal signal. Daniel, you're trolling. Do not flush your pills down the toilet. This is going to cause endocrine disruptors to go directly into waterways and potentially cause these intersex, intergender fish and amphibians. So don't do this. This is not good. This is a way to cause endocrine disruption, and you don't want that. Poor frogs, right? Who wants to have, ovaries developing or testes developing in your ovaries, immature eggs developing in your testes? It's not a good way for a population to continue reproducing. So again, example here is atrazine. Atrazine is an herbicide that specifically causes this effect you can see on the screen to frogs or to amphibians, and it's a problem. What are some other examples? We have DDT. DDT was banned, but that doesn't mean that it's not around anymore. It still lingers in sediments, aquatic sediments and agricultural soils, and it's going to lead to the thinning of the eggshells of birds, as well as causing endocrine disruption. Heavy metals are endocrine disruptors as well, lead, arsenic, and mercury, even though they don't bind to the receptor site. So lead, arsenic, and mercury, they're not going to bind to the receptor site and mimic a hormone, but they're still going to disrupt the endocrine system. They're going to interrupt sometimes menstruation or sometimes liver function and just really problematic from a human health standpoint. Also human medications. So don't flush your pills down the toilet. Don't dump your medications into rivers. You don't want that to happen. And yes, you can't get through an APES review session without referencing the great Rachel Carson. She wrote Silent Spring. It woke us up collectively as a nation to the harms of DDT. This was the early 60s, before there even was an EPA, before the Clean Water Act, when our rivers were catching on fire. So everybody take a moment of silence for Rachel Carson and her contribution to science. DDT is a high key L. And yes, Rachel Carson proved that. And she is the queen of the environmental science movement. So, have a sip of tea for Rachel Carson. All right. On we go to watersheds. Really quickly, we're going to cover these before we get into human impacts on them. Watershed is like a funnel of land that drains into a central body of water. And the impacts that can happen on watersheds are something we're going to go over here in a second. So why are there threats to watersheds? Well, humans put a lot of pollutants into a watershed, things like motor oil or sediment or pesticides, and that can enter the central body of water. So let's go back here for a second. If you have motor oil on this urban area, or if you have pesticides on this farm, we are going to potentially see those draining into the central body of water due to runoff. Now, if you have a really great slope, a really steep watershed, that's going to be especially problematic for any pollutants in the watershed. It's going to drain them faster into that central body of water. And so also, how much vegetation you have and the soil permeability, all of these things are the big three factors that determine how fast does water drain through a watershed and into the central body of water versus how much of it trickles through the soil and recharges groundwater. All right. On we go to other developments or other ways that we can disrupt. We can develop an area. So Florida is famous for this. They have diverted a lot of the water that feeds the Everglades and drastically shrunk the size of the Everglades. To divert water means to dig a channel or a ditch and to take it somewhere else for agriculture, for golf courses, for human drinking water, or even for cooling a nuclear power plant or something. So we divert water. That means there's less downstream. That lowers the level of wetlands. It drains wetlands, and that's going to be damaging to them. We can also overfish. If we overfish a wetland, we lose a lot of the key species there, destabilizes the food web. That's problematic as well. All right, eutrophication. The topic that every ape scholar thinks they understand, but don't actually. Take a look at eutrophication here. Try to understand the actual steps. So a lot of times we jump right to algae blooms and we forget about hypoxia. So what are the steps involved? Algae bloom because of enrichment with nutrients. This could be from animal poop, could be manure, could be human poop, poorly treated sewage or raw sewage, could be fertilizer. It causes the bloom of algae. The algae die. Bacteria in the water break the algae down, and that uses up the oxygen. That's the step right there that everybody forgets. The algae die, the bacteria break them down, using up oxygen in the process. So that is the reason that we get hypoxic waters or hypoxia. Another issue that can cause hypoxia is high water temperature. So we're going to flip back and forth between these two slides for a second because they can kind of be, a little bit of a mini positive feedback loop. Water that's hotter holds less dissolved oxygen. There's an inverse relationship. Water temperature goes up, dissolved oxygen level goes down. That's going to lead to hypoxia. It's going to lead to species that are going to suffocate in the water. They're going to die because they don't have enough oxygen. Now, thermal pollution can cause this. This could just be from hot water that runs off of a blacktop in the summer. Urban stormwater is going to be hot. Could be sewage. Gross to think about, you guys, but sewage is pretty hot. Like a river is probably, 40 to 55 degrees Fahrenheit, maybe 60 if it's super warm. Your waste coming out of your body, your sewage, it's pretty hot, 96 degrees maybe. And even once it's cooled off, it's still going to be a lot warmer than a river. So if you put sewage into water, it's going to warm it up. Let's go back and forth here between these two issues. So warmer water also leads to more algae growth. And so you can have a mini positive feedback loop where warmer water makes more algae growth, and that's going to deplete more oxygen from organisms. They're going to die. They're going to get broken down using up even more oxygen, just kind of reinforces itself. All right, POPs, persistent organic pollutants. These are chemicals that are not water soluble. So they get into an organism's body and then they stay there for a long time. Many of them are also endocrine disruptors, but they basically sit in the fat deposits of an organism, build up over their lifetime. So they do something called bioaccumulation, meaning over your lifetime, you get more and more and more and more and more POPs, and it causes health issues like infertility or hormonal disruption. Examples, we've got all of these examples on the screen. I'm not going to go through all of these individually, but notice a lot of endocrine disruptors are POPs. We also have methylmercury, which we're going to get into in a second. That can bioaccumulate, can biomagnify in food webs. And we'll talk about this here for a second. Yes, rip to the eagles. DDT thins the eggshells of eagles, and it almost drove our national icon, our national bird, to extinction. And then the other thing is, yes, these build up in the fat tissues, and that's going to be the issue. Great question here. What about bioaccumulation versus biomagnification? Simple way to remember it. One organism bioaccumulates versus a food chain biomagnifies. Think of a magnifying glass, and at the bottom of the food chain, it's small, but at the top of the food chain, the organism is really large, and it's accumulated a large amount of that POP. So bioaccumulate, one organism bioaccumulates. So like me, if I get DDT slowly over my lifetime, I bioaccumulate it. I could also be biomagnifying though, because let's say I eat tuna from the ocean that ate a sardine, that ate a krill. The level of mercury, methylmercury specifically, builds up in each organism up the food chain, leading me to biomagnify that mercury. So let's go into a little more concrete way to understand this. Let's say we have PCBs or methylmercury that gets into an aquatic ecosystem. The smallest organisms have just a little bit, just a tiny little bit of it. But what happens is these zooplankton eat a bunch of phytoplankton over their lifetime. So they take in all the POPs of all those phytoplankton. Then this herring, or whatever this small fish is, text is really small. I can't actually even see it. Is it a herring? Yeah, the herring eats the zooplankton, and that's going to lead to the herring building up a higher concentration of this. And then eventually the salmon eats a bunch of herring over its lifetime. So it gets all the PCBs or methylmercury from not only the phytoplankton, but the zooplankton and the herring. And then finally, by the time you get up to the killer whale or the orca, it's going to have all of the POPs from the hundreds and thousands of salmon it eats over its lifetime, and all of the herring that those salmon ate, all the zooplankton that those herrings ate. It basically accumulates all of the POPs that were in that aquatic ecosystem. So what are the effects of this? Well, it's going to lead to sometimes infertility. It can lead to disruption of normal, hormonal development. It's going to be an endocrine disruptor a lot of times. It can lead to cancer. And so you don't want PCBs building up. And then if you ate the orca, you're going to take even more. So the number one way that humans get exposed to methylmercury, well, it's hard to say number one. Don't quote me on that. One of the number one ways humans get exposed to methylmercury is eating seafood, specifically big seafood. You're going to get a lot more methylmercury, a lot more PCBs if you ate an orca whale, which I don't think you could do. They're probably endangered. So if you ate a herring or salmon compared to if you ate like shrimp. All right, I'm going to go to landfills. Remember, in a landfill, we have these important measures to try to limit pollution getting out. So we have leachate collection systems. They're going to collect this water that drips down through the landfill and takes pollutants with it. They're going to take it for treatment. We're also going to get a methane recovery system that's going to pull that methane gas off, potentially burn it to produce electricity. And then we have a clay cap that's going to line after we're done. We're going to put that clay cap on the top and a clay and plastic liner so that we prevent that pollution from leaking out and getting into our groundwater. So these are ways that we can limit the impact that landfills have. Waste to energy is a great way to do. Also reduce the total amount of waste we produce from a volume standpoint. And in the same process, generate electricity. So what we do is either we burn the waste, and this is actually something my students just went and saw. We went to our city's waste to energy facility. It's really wild. Mountains of trash. Like we went up 4 stories, and there's this big open concrete pit, 4 stories tall, like hundreds of feet up. It was more than 4 stories. It was huge, and it was just trash, and it was being picked up by a claw, put into a hopper, and then fed into a furnace and burned. And then at this point, if you guys have been watching this whole video, you got to know the steps here. Heat from burning trash, steam, turbine, generator. So not only are you going to reduce the volume of trash, because the ash that comes out of that furnace that you have to bury in a landfill still is like 10% of the volume or less, maybe a little more, right around 10%. And you're getting electricity. It's like 2 birds with 1 stone. Then we get into producing electricity from the methane. So you can collect that methane gas from your landfill, prevent the methane gas from leaking into the atmosphere, prevent the landfill from blowing up, and generate electricity through the same process. Heat, steam, turbine, generator. You burn the natural gas just like in a natural gas power plant. The only difference is the natural gas came from a landfill through going through anaerobic decomposition. Tertiary, secondary, primary treatment and disinfection of water treatment. Sewage treatment is an important thing to review as well. So in primary treatment, think physical, P for physical. Physically trapping with like a grate or like a screen, any solid waste coming in, any debris like leaves, plastic, large, I hate to say it, but fecal matter can be trapped out by these screens. My students and I also toured the wastewater treatment plant the same day, and it was one of the worst smells ever. It's one of the worst smells. Primary treatment, you guys, they're physically trapping anything that's in the sewage, and it is stinky. Then we typically let it settle with a grit chamber that's going to let sediment or rocks that may have gotten into the water as it's traveled through the sewers. It's going to let that settle out. And then we're going to go into secondary treatment. In secondary treatment, you have microbes added to the water. The microbes are going to actually break down organic matter and decrease the total amount of nitrogen and phosphorus in the water. Then we have tertiary treatment, which is sometimes done, and that can reduce nitrogen and phosphorus levels further so that we decrease the likelihood of eutrophication. And then finally, we have disinfectant, which is going to be UV light or chlorine or ozone. That's going to kill any microbes, eliminate E. coli or other damaging bacteria, and we're going to prevent that from contaminating rivers. Because when you treat your sewage at the end of the whole process, you have something called effluent. Effluent is the discharge from your wastewater treatment plant. It's going to go right into a river. And so you don't want it to contain bacteria. So you have to do that disinfectant step at the end. All right. Someone asked for a long time ago, and here we go, LD50. We are going to take a quick look here at LD50. So on the y-axis of an LD50 graph or a dose response curve, what you're going to have is percent mortality. And the way you're doing this experiment is you're giving a bunch of different groups of organisms, usually mice or rats. You're giving them a certain dose of a pollutant. That's why we call it dose response. So in this case, we might say that 40 milligrams per kilogram of body weight, that was the threshold where the first animal died, where the first rat passed away, unfortunately. Then we have the LD50 level. That's the group of rats where 50% of them died. And so the group of rats in this case that got 100 milligrams per kilogram of the toxicant passed away. That's the LD50. The lower the LD50, the more toxic the substance is, because it means less of it is required to kill 50%. And that's the basic idea here behind an LD50 graph. Yeah, it's not super complicated. Then we have tropospheric ozone. Just one more quick reminder that tropospheric ozone is going to worsen asthma, emphysema, bronchitis. It comes from the formation of, tropospheric ozone formation comes from NO2 being broken down by the sun. That NO2 is emitted by vehicles. Those vehicles, again, they're burning a fossil fuel. They're putting NO2 out of the atmosphere. Sunlight's breaking down the NO2 into NO and a free oxygen atom. And that NO2 combines, or the free oxygen atom combines with O2. You get ozone down in the troposphere, damaging to our lungs. Again, critical for life on Earth in the stratosphere where it protects us. Down on Earth, damages our lungs. Pathogens and vectors. This is 8.15. Pathogens are living organisms that cause a disease, a virus, bacteria, something like that. And they are going to be responsible for infectious diseases. So let's clarify infectious diseases versus like radon, causing cancer. If you get cancer from radon, you're not going to pass it to someone else. It's not like you're breathing out radon. But if you get infected by, sign of the times, you guys, let's just call it what it is. If you get infected by the SARS-CoV-2 virus and you have COVID-19, you have an infectious disease. You have a pathogen in your body and you're breathing it out. That's what makes COVID infectious. It's a virus that can be transmitted by breathing it out. A vector is a little different. A vector carries a pathogen. So if you get bit by a mosquito and you get dengue fever or you get Zika virus, you didn't necessarily get that disease from the mosquito directly. The mosquito bit you, and a protist or a living organism inside the mosquito was actually transferred, or a virus, into your body by the blood that the mosquito, bites, and there's mixing and the proboscis kind of gets in there and it can actually transmit that living organism into your body. So that's kind of a tricky thing to think about. A vector is just a carrier. Same thing with a rat. Same thing with a human. Good question. Are humans vectors of disease? Sure thing. We can transmit, I could cough and transmit the pathogen, the virus that causes COVID, to someone. I would be a vector in that case. Typically, though, the context of that word applies more to mosquitoes and rats. But, if you're thinking strictly of a vector, a human's a vector. All right. I think that's it. Oh, nope. We got one more thing in Unit 8. So in Unit 8, just something to know here. This is supposed to be a GIF, but the slide is static, so it's not moving around. Currently, this is the range of Aedes aegypti, which is the mosquito that's responsible for dengue, yellow fever, Zika virus. That range is expected to change. It's expected to expand with climate change. So a problem that happens with climate change is not only do we have all these issues like soil drying up and agriculture being impossible and sea level rising and flooding coastal communities, but mosquitoes can expand their range further north, or they can live in subtropical places like the US for longer. And that's going to mean that they're carrying diseases further around the globe with them and living for longer. So that is a big problem. We expect, sadly and unfortunately, that diseases that are transmissible by mosquito will increase with climate change. All right. We're going to do a rapid fire Unit 5, Part 2 that we missed yesterday. We're going to go super fast. So this was the end of Unit 2 or 5, Part 2 yesterday. I know you've been asking for it. There's some important topics. We're going to go really quick, and then we'll wrap up in a few minutes here. So overfishing is an issue, not only because we could deplete the ocean of certain fish species, but then the organisms above them on the trophic pyramid, or the trophic level, the food web that depend on them, they die too. So if we take away all of these feed fish here, now the large mammals or the predatory fish or the seabirds that ate them, they suffer too. Their prey, the zooplankton, blossom in their population because they're not being preyed on. They don't have this pressure. And then the phytoplankton decrease because there's more zooplankton. So you have a trophic cascade, this cascading effect down the trophic pyramid. Then we have mining. There's a bunch of different types of mining. Key things to remember with mining: you're going to have habitat loss, topsoil erosion, especially if you do mountaintop removal. You literally blow up the mountainside. You're going to reduce it to rubble. You're going to fill in streams in the river. You have to get that overburden, all of that soil and vegetation out of the way. And so that means you're basically causing habitat loss by getting rid of those trees and causing soil erosion. So those are issues. Subsurface mining is especially expensive, as you have to go deeper into the earth because you're going further down, you're drilling, you got to pay workers more, higher risk of explosion, higher insurance costs, all of those things. Then we have urbanization. So someone asked about this earlier. With urbanization, we have this big trend of people moving into cities. That's going to replace natural ecosystems like the one on the left in this diagram with built up urban ecosystems. When you replace a prairie or a forest, floor full of grass and trees, when you replace that with impermeable cement or concrete, you're going to lead to a lot of runoff and not a lot of infiltration. So make sure you know that term, impermeable. Now, the opposite of impermeable is permeable. So let's go to a solution here. A solution to fix the problem of urban runoff is permeable pavement. It lets the water drip through. Sometimes it's called thirsty pavement. It lets that water trickle through and it can get to the soil and recharge the soil. That's going to decrease the amount of pollutants being carried as runoff into local bodies of water. Permeable pavement is lit. Go look it up. Look up permeable pavement or thirsty pavement, and you'll see this video of a cement truck dumping gallons and gallons and gallons of water onto permeable pavement and just disappears. It's crazy. Really cool. Okay. Why do we want permeable pavement, or why do we want rain gardens or just more parks? Why do we want to decrease urban runoff? The problem is urban runoff carries any pollutant that's on cement or on pavement into a storm drain and then into a body of water like the Chesapeake Bay or like a river. Those pollutants, pesticides, motor oil, sediment, pet waste, anything that's on cement can get drained into your water source. And so solutions, again, permeable pavement, rain gardens, parks. All right. Sustainability, really quickly. There's a lot of hippy-dippy ways to describe sustainability. Sustainability is the ability to use a resource more slowly than it's produced, or using a resource at a rate lower than its rate of replenishment or regeneration. Using it in a way that it will always be available because you don't take it faster than it forms. So for trees, if trees grow at a rate of, let's just say, 100 full-size trees entering a forest in a year, like reaching maturity, if you cut 200 full-size trees per forest per year, it's unsustainable. If you cut 50 trees per forest per year and they replenish at a rate of 100, that's perfect. You're going to be able to do that forever because you're never going to exceed the rate of regeneration. IPM, integrated pest management, really important. Instead of just dousing your fields with pesticides, which are effective but can eventually drive resistance, pests evolve resistance because all of the ones that are susceptible die. The ones that have genetic adaptations that let them survive, they live and pass on their adaptations. Instead of using that process, which leads inevitably to resistance, you can use integrated pest management. It's numerous methods all built in together, one of which is biocontrol, bringing in a natural predator to eat the pest. One of them is crop rotation, which basically switches up on the pest, which crop is going to be in a given field at a given year. So the corn borer lays its corn borer eggs in the soil. It's a cornfield, so they're expecting it to be corn the next year. And you switch it up on them, and all of a sudden they wake up and they're looking around wondering where the corn is, and you planted soybeans. And so they're not quite so happy. Farmers are happy because they're not going to eat the soybeans to the extent they're eating the corn. You can also plant intercropping or use intercropping, kind of like plants that may repel pests. Certain plants will give off a scent or like an odor that's going to repel the pest and protect the crops that you're harvesting. How do you also use crop rotation for soil fertility? This is really key. Different plants have different nutrient demands of the soil. So corn is notoriously nitrogen demanding. It's going to take a lot of nitrogen out of the soil. So you could alternate corn with a legume. Legumes are like soybeans, beans, peas, and those are going to actually fix nitrogen from the atmosphere. So let's go back to the nitrogen cycle. What was that whole acronym? fix, nap or panda, something like that. But nitrogen fixation is going to happen because those bacteria in the root nodules of legumes are going to return nitrogen to the soil. You can also use a leguminous plant like a cover crop. And so that way you're going to just cut the plant residue down, leave it on the soil. One, it's going to stabilize and anchor the soil with its roots and its crop residue. It's going to sit like a moisturizer on the soil. But two, it's going to decompose, break down, and give its nutrients back to the soil. So then you can grow lots more corn the next year. Here we go. Here's our nitrogen cycle again. Fix NAAD, ANPAN, and PAN. So the fixation is the critical part here. The bacteria in the root nodules are going to fix nitrogen. They're going to take it from N2 gas in the atmosphere, turn it into ammonia in the soil. So there we go. All right. On we go to one more quick question. Somebody asked a question about limestone. This is important. Limestone can buffer the pH of soil. So if you have acidic soil due to acid rain, you add limestone to it, and it's calcium carbonate that's going to act as a base. It's going to buffer those H plus ions, absorb some of them so the soil is not so acidic. That means your soil is going to be more nutrient rich because H plus ions displace a lot of positively charged nutrients in the soil. They also make aluminum more soluble, and there's aluminum naturally occurring in rocks. And so you don't want aluminum soluble in your soil. You want your soil to be nice and buffered. And so limestone acts as a buffer. Okay, a solution to overfishing could be aquaculture. You could grow fish in nets. That's going to reduce the amount of fuel you need because you don't need to go out far into the ocean to catch them. You're also not going to use as much space, and you're not going to damage local populations with overfishing. Drawbacks of aquaculture: sometimes your fish escape and they can pass diseases on to basically, wild populations of organisms. But you also have a lot of waste buildup and a lot of hormones being given to the fish, antibiotics. So all those things can be released through the water and can contaminate wild populations. That's an issue. Not to jump around too much, but I do want to go back for just a quick second. We talked about limestone being crushed and added to soil, but scrubbers may use lime as well. Lime is going to neutralize ammonia. It's going to limit your NO2 production. They may use limestone as well in a solid state. I'm not familiar with state-of-the-art scrubbing technology, but certainly lime is used in some scrubbers, and that could neutralize some of your NOx. Not sure about SOx. I think that's more calcium oxide that they use, but you can definitely use a wet scrubber for NOx or SOx. All right. I think, there we go. I did have some of the aquaculture drawbacks. So just like I mentioned, you can have some of the same issues of CAFOs on land for aquaculture. One other kind of pro tip to think about is that in aquaculture, you are going to a lot of times have deforestation actually to cause it. What do I mean by deforestation? I mean mangrove deforestation. So cutting down mangrove swamps to have shrimp farming, that's a big problem that destabilizes the coastline. And so that's definitely a big issue there. All right. Let's see. Let's take a quick moment to check in on a couple comments here. This is just kind of interesting because I love, teacher YouTube. So I want to just address a couple things real quick. We are winding down to the end of the night. But AP Bio, obviously Bozeman. So Paul Anderson, Bozeman Science, is the unquestioned GOAT of teacher YouTube, in my opinion. He's the best. He does science videos, and he is just amazing. So Bozeman has lots of great content. Fun kind of insider baseball thing. I got to meet Paul Anderson. So I got to meet him and pick his brain a little bit about making apes videos. He made an AP environmental science series a long time ago before the course redesign. And so it was really cool to meet him and pick his brain a little bit about apes. He gave me some tips on making videos. And he said, just keep going with it. Looks like it's going well. And it was just so cool. It was like meeting one of my heroes. So yes, Bozeman, you guys know Bozeman is GOAT of TeacherTube, especially teacher science. But someone asked about science or about bio, sorry. So AP Bio Penguins. Not a YouTube. Well, I think she's on YouTube a little bit, but Instagram is where she really shines. So she does tons of AP Bio reviews. So go check out AP Bio, um, AP Bio Penguins if you're interested. Really good stuff if you're taking it, if you happen to be taking AP Bio this year or next year. And then we have just a couple more questions. I think it's fun to wrap up here with some questions. This is my 8th year teaching apes. So I have learned a lot about it. I've graded exams for a couple years, but I love that there's always more to learn. There's always more to learn about apes. And so this is kind of a fun comment too. There's totally an apes teacher Facebook group. We're together as a group. There's like thousands of us in an apes Facebook group. And so that's a big community that I really respect and learn a lot from. So I have been teaching apes for close to 10 years, but there's people in that group who've been teaching it for 20 or 30. And I get to ask them questions about it. Well, 1999 was the first year apes was run, actually. So not quite 30 years, but there are people who've been teaching it for close to 20 years. And so anyway, it is kind of fun to know that there's a big Facebook teacher group. We all get together and brainstorm the best ways to teach eutrophication and stuff like that. So anyway, good question. And then one final question, the most important, is water wet? Yeah, totally. Water's wet. Water's as wet as it gets, because to be wet, like the verb wet or the adjective wet, I mean, is to be covered by or in contact with water. And water molecules, if you know anything about hydrogen bonds, my goodness, AP Bio scholars, where are you? Water is bound to itself. It has cohesion. It's this unique property. And so really, like, AP Bio people especially, it doesn't get wetter than water. Water is as wet as it gets, because unless you get a water molecule by itself, a single water molecule, I suppose it's not wet. But as long as there's two water molecules touching each other in a hydrogen bond, hydrogens to oxygens, water's wet. So there we go. Let's put the kibosh on that one. All right. I think there's actually one more topic, you guys. Fire suppression. Let's wrap up here with fire suppression and controlled burns, and then we'll call it a night. So ironically, by stopping wildfires, we actually make them worse in the future. And so that's because we have all this dead biomass building up. So you get all this dead biomass building up on the forest floor. Then when you get a fire, now you have all this ladder fuel. Ladder fuel are like medium-sized dead trees that can take the fire from the floor up to the medium-sized trees and then up to the crown of forest. So it can actually lead to a crown fire, which is the worst kind of fire. And that's going to lead to the devastation, and it's going to lead to a forest taking way longer to recover than if it's just a floor fire. So how do you stop really bad fires? You do a prescribed burn. So you go out and you purposefully burn up a lot of the dead biomass. One, you cycle nutrients. Two, you make room for new growth to occur. And three, you prevent that fuel from building up and fueling bigger fires in the future. And so that is prescribed burns. So just as a quick recap, if you're watching this, last night we did about 2.5 hours of live stream and we covered units 1 through 5. Tonight we're at 1 hour and 50 minutes of live stream. We covered units 6 through 9 and the part of unit 5 we hadn't covered. So we have basically covered, you guys, in a couple hours. Not in total detail. We had to leave some things out. We covered almost everything. So that's kind of crazy if you think about it. Just as a reminder, there is one more review tomorrow, but the review tomorrow is just for folks that are purchasers of the Ultimate Review Packet. So if you're looking for one more reason to consider, checking out the Ultimate Review Packet, checking out some exclusive review resources, you can do that. You can purchase it, and that's going to give you one more live review session that's going to be specifically posted there. So if you've already purchased the Ultimate Review Packet, there'll be a section there. You can check tomorrow to be posted. But I will be live tomorrow on the Marco Learning YouTube channel at 6. And so if you want some more live stream review on YouTube, check out Marco Learning tomorrow. I'll make sure to post on TikTok, Instagram, post on the channel here, schedule a live and everything, so that you know exactly when that stuff is going on. But then there will be a specific kind of exclusive live that's just for people that are subscribed to the Ultimate Review Packet. That'll be from 7 to 8 p.m. tomorrow night. It'll be more Q&A style, so it won't really be content review as much. It'll be FRQ tips. It'll be more Q&A style. So thank you guys so much for showing up. A couple more questions that are popping up. You don't need to know Simpsons and Shannon. If you know this, that's cool. You have a teacher who kind of went above and beyond, but you don't need to know that one. Yeah, the calculator TikToks that I made, I'll try to get those pulled off of TikTok and put onto YouTube. They are already on TikTok. If you don't use TikTok, I respect that. It's a crazy platform. I don't really want to keep using it. I used it during APES exam review, but it's crazy. I think you can actually look at it though on the web without getting the app. So if you search like Apes versus Everybody TikTok, you could probably see those calculator videos, but I'll try to pull it off and put that on here. And then as a quick recap, what are the things I recommend doing like tonight, tomorrow? I highly recommend writing those 2021 practice FRQs that are on. I wouldn't even call them practice FRQs. They were last year's exam FRQs. Go to AP Classroom or just search APES FRQs. If you literally just in a URL, in your browser, just search APES FRQs, it'll be the first link. Look at those 2021 FRQs and write those. That'll be really, really helpful. All right. Thank you so much, everybody. It's been wonderful reviewing with you all. If you get featured in the live streams, are we immortalized on the channel? I guess so. I guess if your comment popped up on screen, it'll live on for APE scholars, for generations to see. So thanks so much for showing up. Thanks for asking great questions. And if you're new here, you may not know yet, but if you have seen any video, if you've been part of the channel to any degree, you know how we wrap things up. First, though, we give poetry snaps, round of applause, whatever you want to do for Kyra. Give it up for Kyra. She is a certified, verified 5 earning APE scholar last year, even in a pandemic year, even in a virtual year. She went above and beyond and just did awesome on the APES exam. And she went even further above and beyond and has come back to moderate the channel. And extra shout out to Kyra today, not just for moderating, but like she was constantly feeding resources to you guys. She was answering questions. So to have an experienced APE scholar who knows their stuff come back to the channel and just fuel us through the live stream while I'm busy looking at the camera and slides and forgetting to look over at the comment section, indispensable to have her there. So again, poetry snaps, round of applause, virtual claps, whatever you do to show appreciation in the chat to her would be wonderful. But as I was saying before, if you're new here, you got a lot of videos to watch. But if you've been a part of the channel, if you subscribe, if you chat, if you comment, you know how we end things. And that is think like a mountain and write like a scholar. Have a good night, everybody. We'll see you tomorrow.